I hope everybody is doing good, staying safe with your family in this COVID situation, and studying at home. Uh, I hope everybody is safe. Let's get to the topic. We're going to be discussing about transmission gate logic style for designing the logic circuits. All right. Let's have a look. Let's revise what we did in previous lecture. We discussed about pass transistor logic. Those who have not watched the previous lecture, please do. I recommend you to watch the pass transistor logic lecture for understanding basic concepts about the pass transistor logic. Okay, this lecture is the following lecture in the same lecture series about designing the logic circuits. Good. So we have seen how we can use the PMOS and NMOS. Okay. In terms of pass transistor logic, we typically use NMOS for better characteristics than than PMOS when we develop circuits using pass transistor logic. Depending upon, sometimes you may have a situation where you don't have any other alternative other than using the PMOS as a pass transistor logic. But in general, NMOS is preferred choice. These concepts we have discussed in previous lecture. We have also established the fact that when the PI, which is the gate control, is 0 for PMOS, it produces a stronger one. All right. And when the gate control PI is 1 for NMOS, it produces a stronger 0. So remember that these are two important characteristics we're going to be using. Good. We also have discussed about what are the advantages of pass transistor logic and what are some disadvantages or drawbacks. One of the drawback is that the output voltage is not actually exactly the high logic level, but slightly less. So we approximate it with with the minus of the bias or threshold. Okay. Actually, it's not exactly the threshold. It's bias as well as some other voltage. So we approximate it in terms of VTN. Okay. Now, if you want to go dig down in detail with respect to particular technology, you might get very complex equation of it. So instead of going in too much maths complexity for understanding the basic concepts, let's stick with, we approximated the output voltage, which is slightly less than the actual high voltage. So that's a little drawback because we need to scale the voltage of the output somehow, okay, to make it proper logic. So how we do that? Either we use some kind of a level shifter or some kind of a buffer or inverter, some kind of a circuitry at the output. Okay, doesn't matter what you want to use it, depending upon what design requirement you have. Okay, for understanding the concept, since the voltage will not be exactly as the required high voltage level, will be slightly less, we're going to be needing an extra circuit. Good. All right. Now, what is the alternative? What is the alternative so that we don't need an extra circuit at the output? So if we think about it, what is the alternative we can have? We come up with some kind of logic structure. Okay. Before going to that logic structure, let's review it. So we have PMOS and NMOS, and typically you have seen in textbooks this structure of the PMOS, okay, is rotated 90 degrees. So this structure you see in textbooks. So in my lecture, I have just put it straightforward, but nevertheless, it's all same. So you kind of, whatever we were using, we rotate it 90 degrees. So we come up with these structures for PMOS, okay, and for NMOS. Very simple. All right. Now, what if we connect the terminals of PMOS and NMOS together? Okay. So we come up with a structure or a circuit. And what if we connect the NMOS to the gate control, PI, and the PMOS gate to the inverted version of the PI gate control? Okay, so that's very interesting, okay? So this is called a transmission gate structure. All right, now let's see what happens. So what happens when PI, that is a gate control, tends to 0, okay? Then when it tends to 0, inverted version of the PI will tend to 1. And it's an NMOS, it's an PMOS here, so that will block, okay, the current flow, or or the holes flow through the channel, okay. In reality, it may not block 100%, but will block significantly so that the output will become Z, or sort of high impedance, okay. So in other words, if you have seen the water analogy, where we have the big tank of water here at the one end, so the water will be blocked. This will block the water flow. I have discussed the water flow analogy. It's a very good concept of water flow analogy when you design the circuits, okay. So how the water flows in pipes from the tank, and very similar characteristic how the current flows in the wires, okay. Please watch that lecture. I think I discussed in 2 or 3 lectures the same concept of the water flow analogy of the electric current flow. All right. So we have seen here that when the PI tends to 0, this is going to be blocked. Now what happens to the NMOS, okay? So when PI tends to 0, what happens to the NMOS, okay? So NMOS will be blocked. We have seen that how the NMOS works. So it's going to work when PI is 1, but here we are saying PI is 0. So this will be blocked. So there won't be any water flow here. Good. Now what happens, remember this equation? Second, what happens when PI tends to 1? So let's look at when PI tends to 1. Inverted version of the PI tends to 0. Means that now if we have a water reservoir here or water tank here, this gate will be like an open channel, okay. So this will allow water flow to the other end. In case of the PMOS, the holes carry the charge, right, and the electric current flows. So whatever is at the node I, that voltage level will become at the output node, okay. Now let's look at what happens at the NMOS here, okay. So in case of NMOS, PI is high, which means that this channel will be open, okay, and water will flow, or current will flow, or electrons will flow from one end to another and carry current, okay. So whatever is the logic level at I will become logic level at F, means that this NMOS is conducting, so as the PMOS is conducting, okay. Remember this fact, important. So what we gather here, that we have a rail-to-rail switching, or we can switch the voltage from logic level 0 to valid logic level high. So what happens that this becomes PMOS, gate control of the PMOS becomes 0 when PI is 1, and so as the gate control becomes 1 for NMOS. And PMOS, as we said earlier, that PMOS is good for producing a stronger 1. So if the I is 1, PMOS will conduct and will produce logic 1 at the output. And NMOS is good for conducting the logic 0. So let's say we have, input is transiting to logic 0. NMOS will conduct. Will produce a stronger one. Sorry, will produce stronger whatever is the one terminal to the other terminal. Okay, so if we are saying that I tends to 0, so as the F tends to 0, and it will be strong. Okay, so strong means that there is almost no loss of the voltage level at the output. It will be high voltage level. So we don't need any other extra circuit to scale the voltage level at the output. That's what it means. Okay. Now let's look at the when it tends to 1. Okay, it tends to 1. So for the 1, we already said that PMOS is good. Okay, so then when it tends to 1, this PMOS will be producing a stronger 1, and output will go to 1. All right, so as you can see here that we have used PMOS and NMOS, both of them. PMOS for transferring or transmitting logic 1 from input to output, okay, and NMOS for transferring logic 0 from input to output. Or in other words, this gate is sort of its purpose is to transmit a logic level from the input to output and maintain the logic level at the output node so that no extra circuit is required. Okay, so we established what is transmission gate. All right, good. So we call it rail-to-rail swing of the voltage. Okay, the very important fact. Now, since we have, using the both NMOS and PMOS, and PMOS typically has twice the area of NMOS. So let's say twice the area of NMOS. So it's a bigger one. Circuit is bigger, and then we are connecting both terminals together. And if we don't have the inverted version of the control PI, then we might have to use inverter. Okay, so we might have to use inverter if we don't have inverted version. Okay, so depending upon how you design the circuit, but transmission gates typically tend to have little larger area, higher capacitance. Okay, that's little drawback here, that higher parasitic capacitance compared to pass transistor logic. But the added advantage is that we don't need any extra circuit at the output. Good. This is one of the symbol of the transmission gate, as you might have seen in the textbooks, that 4 triangles, right, with the circle. So above one in my picture is PMOS, and the lower one is NMOS. Okay, and we already know NMOS we use for driving the stronger logic 0, PMOS for driving the stronger logic 1 level. You might have also seen this structure at the bottom. Both of them are correct for showing the transmission gate. Okay, here it's more explicit that PMOS and NMOS, they are connected together, very similar to what is shown here on the right side of the good. Now let's look at remember these equations. Let's look at some more interesting facts. Good. So now let's try to develop a circuit for a multiplexer. Interesting. So what the multiplexer does, depending upon the select input. Okay. So here select is select input is PI. Okay. Or gate control, you may call it S. So if the select input is 1, it will transmit whatever is on the I1 to F. And if it is 0, whatever is on the I2 to F. Okay, we can write in form of the equation that whenever Pi is 1, so 1 and with I1, so whatever is I1, right, that will tends to F, because when this is 1, this inversion version becomes 0. Okay, so this whole I2 multiplied or ended with I bar will be 0. Okay, so you end up transmitting I1, okay, to output side when Pi is 1. Similarly, when Pi is 0, so this becomes 0, then whole this becomes 0. Okay, so you end up this an inversion version of the Pi becomes 1, and then you transmit to the output side whatever is on the I2. Good. So basic equation, there is no complexity here. All right. Now, how we can use transmission gate, okay, to make a circuit of the multiplexer. Let's look at it. Okay. So we have, let's say, 2 transmission gates. Okay. One transmission gate is for transmitting the I1 to the output, and another transmission gate is to drive I2. Now, if we connect them in this manner, okay, that the control Pi, right, is connected to the NMOS gate, and inversion of the control Pi connects to the I1 PMOS. No problem here. Now, second structure, we connect the inverted version of the Pi to the gate of the NMOS. So this is important fact here, right? So we connect inverted version of the Pi to the gate of the NMOS, opposite to what we have of the I1. And we get the output. Okay, now let's look at it, what's going to happen. So let's see the truth table of the multiplexer. Okay, so when we have Pi is 1, okay, we are transmitting I1. So I1 equal to F, as you can see here. All right, Pi tends to 1, I1 tends to 0, and F tends to 0. Very good. Now let's look at the PMOS for driving the 1. Okay, good. All right, now, so what happens here that, let's go back. What happens when Pi is 1, we drive it, okay. In both the cases, whether we have I1 0 or 1, when Pi is 1, it's driven. Now what happens here at the second transmission gate? Since the Pi is 1, that will become 0. Okay, so this will become 0, this will be off. Okay, and for the PMOS case, Pi is 1, that will also be off. So this I2 will produce, right, this transmission gate for the I2 will produce high impedance G, but then we are getting a stronger logic level 1 from the I1, and the stronger 1 will dominate, and we will get a function output F function of 1. Now you might see, right, you might have seen in textbooks that the characteristic equation is, if we put a graph, like when the voltage is going from 0 to 1, 1 to 0, so you might get such kind of graph for transmission gate. You can check in the textbook, but that's more like a fine characteristic, which, you know, we can do small circuit and do SPICE simulation and get graph. So that's fine. The important concept is how to connect, how to make use of the transmission gate for designing the logic circuits. Okay. Now let's look at what happens when the PI control is 0. Okay. When the control is 0, we see that the F follows what is on the I2. Great. Now let's look at what happens when PI is 0. If I2 is 1, I2 gets transmitted to output. Okay. So what will happen that when PI is 0, okay, this gate will be on, and inverted version of the PI is connected to the gate of the PMOS of the first transmission gate I1, and that will be off. Okay. And then the PI, right, since we have a second option, we are connecting PI to 0, and the 0 is connected to NMOS gate of the I1, and that will be off as well. Okay. And this will produce a Z value, high impedance value. But since the bottom one will be on, okay, and this value will dominate whatever is on the I2 when PI is 0. Okay. Now let's look at what happens when the I2 is 0. The NMOS will produce a stronger 0 at the output. Good. Okay. So what we see here, that that we can connect two transmission gates together to make a multiplexer, okay, or in form of a second picture which we have seen earlier. Instead of using a 4 triangles, we can use a square, right? A square, and with a bar on both sides. Okay, same thing, right? Two different pictorial representation of the transmission gate multiplexer structure. Okay, now important fact, another important fact here. See how many transistors we have here. 1, 2, 3, and 4. So we have used 4 transistors, provided that we don't have to invert the control PI. We already have available inverted line of the select input. So we use 4 transistors, 2 NMOS and 2 PMOS. Very good, right? Now, what if we don't have the inverted version of the select input? Then we will have to invert it, okay? And inverter, right, takes the 2 more gates. So now how many gates we will have now? 1, 2, 3, 4, 5, 6. So we'll have the 3 NMOS and 3 PMOS, 6 gates, right? That's a small difference, right? So usually when you do big circuits, you invert select line, use one inverter, and then you keep on using the same inverted version for subsequent transmission gate structures. So you invert one, and then you keep using this structure in series, so it becomes like a series. You can model it with the RC lumped model if you have more transistor, that transmission gate structure, right? So it will become like multiple resistors in series for complex logic gates, right? Or in parallel, right? So you can develop an equivalent RC circuit delay model for that. Okay, so we'll be discussing that in coming future lectures. But for now, to understand the concept that, right, you will need less gates, less PMOS and NMOS, but the structure of the transmission gate is bigger compared to regular PMOS. Will have compared to regular pass transistor logic, and will have more parasitic capacitance. Okay. Okay, so let's see some of the just 3 advantages what we have. I mean, we can have many more advantages, but 3 key important points for transmission gate. first important point is the full rail-to-rail swing. That's a very important point, that we don't need any extra circuit at the output. Okay, second important point is they have larger capacitance associated with them. Okay, PMOS is roughly twice the NMOS, and then they're both connected, so there will be coupling capacitance, there will be capacitance to substrate, there will be different capacitance associated with each node. We are not going in detail for those capacitance, but you can look in the textbook. A larger capacitance, more parasitics, more power consumption, and so on. So capacitance is a big mess in circuit design in VLSI, right? Okay. Then another important point is, as we said, that larger capacitance, right? It will have it will need more energy to charge and discharge. More power consumption will lead to, okay, and that will lead to more power consumption is more the thermal issues, right? So it will have a higher temperature, right? Its thermal profile will be much higher than pass transistor logic. So some drawbacks, okay, some advantages, rail to rail swing, but some drawbacks. Okay, now let's look at some of the applications where we can use analog circuit designers. They use heavily, they love this structure of transmission gate. The fact is that the I input can be of analog in nature, not only in digital. So I doesn't have to be a logic 0 or logic 1. It can have any value, and which analog designers love it, that they can transmit any value from the input to output. So they love transmission gate structure. And I gave example of multiplexer. There are many other circuits where analog designers use transmission gate structure. Flops and latches also in those circuits, transmission gates are used, and memories, to separate out the address and data lines, and to have a tri-state buffers and all. A list keep on going for applications. Okay, so depending upon what applications we have, we use different circuit design styles. Okay, there is a trade-off, right? Trade-off between power consumption, between area, parasitics, how much noise margin we have, bunch of things. Okay, so we discussed about transmission gate logic concepts, basic ideas about transmission gates, some of the key applications, some of the key characteristics, some of the key advantages, disadvantages of transmission gate. All right, thank you very much. I hope you have enjoyed this lecture. Leave me your comments and suggest me some more topics which you would like to learn. Thank you once again. Have a wonderful day, and please do like, subscribe, and these days YouTube has since long time the bell icon. So press the bell icon so that you get the notification immediately. Thank you for encouraging and supporting us. Have a wonderful day. Bye for now.